Okay, so here we're going to take a look at finding areas between polar curves, right? Or just area of polar curves, right? So we're going to integrate polar curves. So to kind of see where the formula comes from, we start with generic, or just a straightforward circle here, and we're going to look at a sector of a circle of radius r. Right now, the sector formula is 1/2 r squared theta, right, where theta is in radians again. All right. Now, how does this transfer to our polar graph? So let's say if we just had a general, just polar region, right here, looks something like that, right, where this angle is A, this angle is B. So the idea here is similar how when we had Riemann sums, we broke it up into smaller regions. And here we're look at a region small enough where, if we call this the change in delta, it looks like a sector in a circle, right? Where if we partition it, right, where we call this just a general theta I minus 1, and then this one theta I, right, that we can calculate the area of this ith region to be approximately 1/2 using the area formula, right? Where the r is actually a function of theta, right? In polar coordinates, f of theta sub I star squared, and then theta would just be delta theta, right? The thickness of that sector. Okay? So that's kind of the idea behind it. And the idea is that, all right, well, how do I find the area of the whole region? Well, the area can be approximated by having some kind of Riemann sum, 1/2 f of theta sub I star. And this theta sub I star is just the way you want to think of it, is just some theta in the desired interval, right? Maybe it's the one in the middle, but it really doesn't matter, because as we'll see with the Riemann sum that we take, how do we make our limit, or excuse me, our area more accurate, is we have more and more of these segments, right? So the area can actually be found by taking the limit as n goes to infinity of the sum of all these. F of theta sub I star squared delta theta, right? Well, we know from first semester calculus, right, this converges, right? If it converges, which here we can just assume that it does, as long as the f of theta is continuous, to the definite integral f of theta squared d theta. Right, so that is how we would find the area of our polar region. Right, so let's take a look at some examples here, right? So here I want to find the area enclosed by one loop of the four-leaved rows r equals to cosine 2 theta. Okay, all right. So here we could see a graph of it. Right? So it looks something like this, right? All right, now a couple things here to realize is, okay, well, I need to set up the integral here, right? So the integral will look, the area is going to be, so I just need one leaf of the rows, cosine squared of 2 theta, right? That's my f of theta, right? Usually some equation where you have r equals d theta. Right, now here what we want to identify here is that when theta is 0, right, we start off here, right? Cosine of 0 is 1, but then it starts to decrease, so it takes this path here. Excuse me, this path around here. Okay, so the lower limit will definitely be 0, and then as it gets back to 0, well, that would be when cosine is pi over 2, but in this case, since it's 2 theta, when the theta becomes pi over 4, right? So that's only half of the leaf though, right? So I need the full leaf. So I can approach this one of two ways, right? I can either have the integral go from negative pi over 4 to pi over 4, right? Again, going in the graph here, if this is my starting position, the negative pi over 4 would be in this direction, right? Where it starts at 0, then it gets traced out here till it gets back to 1, to the origin there, to the pole. All right, and that'll give me the area, this whole area here, the whole leaf. Or I can use symmetry since it is symmetrical, and I can do this is the same as, oh, excuse me, I forgot here my part of the formula, 1/2, right? So I can do this, or I can do double from 0 to pi over 4 of cosine squared 2 theta, d theta. Okay, which I'll do, right? Just I always like when the 0 is part of the limits, it makes it easier to evaluate, right? So what that does is, here looking at this graph, it essentially, the region here that I'm integrating is in that first quadrant, this part right here, and then I'm doubling it to get the full leaf there. All right, so we'll go ahead and work with this integral here. So now it becomes the integral from 0 to pi over 4 of cosine squared 2 theta. Okay, now whenever I have, so now techniques of integration here, this is a basic one. There's no substitution I need to do because it's just cosine squared. So we need a power reducing formula. So the power reducing formula is 1/2 1 plus the double of the angle. So it's cosine 4 theta. Over 4 d theta. Okay, and now this becomes 1/2 integral of 1 is theta, right, respect to theta, and integral of cosine is sine of 4 theta, but don't forget it's 4 theta, so divide that constant out right there. And this will evaluate it at pi over 4 and 0. Okay, so 1/2, plug in pi over 4. All right, when I plug in pi over 4 into 4 theta, it's sine of pi, so that's 0. And then the lower limit minus 0, sine of 0, also 0. So what we have is really just pi over 8. So that's the area, pi over 8 square units of one complete leaf right there. All right, and that's how we apply the formula, right? Let's do one more example here. All right, so for this example, I want to find the area of the region that lies inside the circle r equals to 3 sine theta and outside the cardioid r equals to 1 plus sine theta. All right, so first let's get a picture here of what we're looking at. So we're looking at this right here. All right, so inside the circle, so this region, so I couldn't, Desmos didn't allow me to have a 3-part inequality involving r and theta. So I couldn't shade it in Desmos here, but here using at least the polar coordinates. So inside the circle here and outside the cardioid up here. All right, so this kind of shaded region here. So my graph here, we're looking at this region right here. So same when we had x and y, we can think of it as a difference. Right, we can subtract the areas here, so we'll have, using our area formula, 1/2. All right, A equals, I'll get to the limits in a second. Right, the top one would be r sine of theta squared minus the inner one, right, which will be 1 plus sine theta, that quantity squared. All of that in d theta. Okay. Now, one thing to realize here is when we do this, right, when theta starts at 0, so the graph of the cardioid starts at 1, right? When theta is 0, r is 1, and then it sweeps up here. And you could see here, they're labeled for us on Desmos as pi over 6 and 5 pi over 6, the region of integration, or the limits of integration. But again, if you didn't have that, you can always just set these equal to each other, right? You could say, oh, excuse me, not r sine theta, 3 sine theta. You can always say, all right, 3 sine theta, when is that equal to 1 plus sine theta, the curves, right? And solving for sine theta, when is that 1/2? And looking at the theta here, it's between 0 and pi. So when sine of theta is equal to 1/2, that's when it's at pi over 6 and 5 pi over 6. So that'll be my limit of integration, right? So the integral that I'll be solving would be 1/2 the integral from pi over 6 to 5 pi over 6 of 9, and I'll go ahead and multiply this out. Sine squared theta minus 1 minus 2 sine theta minus sine squared theta. Okay, and then combining like terms, 1/2 pi over 6, 5 pi over 6, 8 sine squared theta, minus 2 sine theta, minus 1 d theta. Okay, so again, these two sine theta minus 1, straightforward integral. The sine squared, again, we're going to use a power reducing formula. All right, it's similar to cosine. The only difference here is when it is sine, it's a minus, so it'll be 8 times 1/2 1 minus cosine of 2 theta minus 2 sine theta minus 1 d theta. All right, distributing the 8 and, oh, excuse me here, 8. Like this. All right, so here we'll get 1/2 pi over 6 to 5 pi over 6. So that'll be 4 minus 4 cosine 2 theta minus 2 sine theta minus 1. And then we have one more like term here, 4 and 1. So we get 1/2 pi over 6 to 5 pi over 6 of 3 minus 4 cosine of 2 theta minus 2 sine of theta d theta. Okay, now finally here I can integrate here, and we get 1/2 3 theta plus 2 sine of 2 theta. Right, we have to account for that 2, so I divide by 2, and then the integral is minus sine, and then here minus 2 cosine of theta, evaluated at 5 pi over 6 and pi over 6. Okay. All right, so we get 1/2, this becomes 3 times 5 pi over 6 plus 2 sine of 5 pi over 3 by reducing here, minus 2 cosine of 5 pi over 6. Okay, and then the lower one will be minus integral here, so here 3 times pi over 6 plus 2 sine of, what do we have here? Sine 2 pi over 3 minus 2 cosine of pi over 3. Pi over 6, excuse me. Okay, so let's simplify here. So this becomes, all right, we're almost there here. 1/2 sine of 5 pi over 2, sine of 5 pi over 3, that's in quadrant 2, 4, so that's negative 2 root 3 over 2. Okay, and 5 pi over 6, that's going to be negative, it's in quadrant 2, so plus 2 root 3 over 2, and then minus here, and sorry, all this gets multiplied by 1/2. So here minus pi over 2 plus 2 sine of pi over 3, that's going to be root 3 over 2 minus 2 root 3 over 2. All right, and then you see in both of these cases, those terms go to 0. And we get 1/2 5 pi over 2 minus pi over 2. So that becomes 2 pi times 1/2, simply pi, right? So that worked out nicely there. Okay, so that is how we would approach a problem that we have area between two polar regions.